Welcome to another session. Yesterday was gone, so today I'm restarting it. Okay, so here is a really interesting problem. So we have this elevator. You might say this elevator, and there's some kind of wedge, and you put a block. So we just want to look at these blocks. You can even take a mass m. Mass will cancel out in this problem. So, but the elevator itself is accelerating. So the block wedge. So this part is called wedge, and that's the block. So and this surface we're going to take it as frictionless. Okay. Now we want to know this is given, this angle is given, so find acceleration, an acceleration vector. That's the one I need to find of that block. For wedge, we already know if the elevator is going up, so this will be the acceleration of the wedge also up. So we have done problems like, you know, if this is a wedge and you put a block there, and if this guy is acceleration is 0, then you have done how to do it, right? This one is old problem. So this you should know, this old problem. It's done, I've done before. Okay, so this is a classic, and here there's no problem. You set up a coordinate system that's, you can set up a coordinate system like x and y, or you can set up a system x prime, y prime, and maybe even this way, y prime, and that's the origin here, origin prime, and this is origin O. So you can set up a coordinate system like that, or like that, and this coordinate system is inertial. So two inertial coordinates, these inertial coordinates, because they're not accelerating with respect to a absolutely fixed frame, right? They're not accelerating with absolutely fixed frame. So here what we're gonna have to do is, we can't do that because this thing is accelerating. Neither of these two frames will work. So in this case, I will have to have a third frame. So I'll have like a ground frame. So this is the ground. So this will be my inertial frame, tied to ground. So this will be inertial frame. This will be my y-axis. This is the x-axis. At instant t, this block and wedge will look like this. At some instant t, the block will be over here. Of course, this angle theta. I mean, the wedge will be there, and the block will be somewhere here. So I want you to pay attention to what I did. I imagine at instant t, what the system will be. It will have some acceleration down the incline, right? But the incline itself is going up. So we will say something remains constant. You can see if if I look at this, say this is y, and this is h, and this part is w, then h over w is tangent theta, and this remains constant. If the block was over here, this h and this w, the ratio will be tangent theta. So this is called constraint. No matter where the block is on this wedge, it must follow a constraint like that. And this is some time t, and this is some time t. But these are not the coordinates going to work out. So from the coordinates, we need to find that, okay? So let's see. There are several ways to put it up, okay? And this one way I'm going to do may not be the most natural way for you. So this is the origin, and this part, this point, this level, I'm going to call it capital Y. Of course, this is function of time, and d square capital Y dt square is a, and that's given. Okay, and I'm going to coordinate of center of this guy, center of mass, just put it like this over there at some point. I'm going to call this x, y, and these are functions of time, right? Because this is at instant time. So from here all the way here, that's the y. That's how far is the y. And from here to here is x. So get w, I'll just assume that from here to here, the bottom of the wedge, let's call bottom of the wedge, I'm going to call it b. Okay, so at any instant, so we say h is going to be y minus capital Y, and w is going to be b minus x. So this constraint translates into y minus y over b minus x tangent theta. So you can bring this on the other side, and so I have a y minus y is b times tangent theta, and this constant, b is constant, tangent theta is constant, minus x tangent theta. So this is the only time dependent, and this is constant. So this is time dependent, and this is time dependent. So if I take a two time derivatives, so this will mean d square dt square minus d square dt square. This will be 0 dx dt d square dt square tangent theta. So what this is telling me is, in this problem, a vector is ax, ay. So these components, of course, az is 0. Okay, ay minus this I'm calling a equals to minus little ax tangent theta. So ay is a minus ax tangent theta. That's the relationship. So actually, if I just find ax, I can find ay, both of them. So over here, I just need to find one of them. I just need to find a minus ax tangent theta. So we just find ax. Okay, how do we find ax and ay? Well, need to write equation in motion. So let's draw that wedge here again. On that wedge, you already know this. The wedge will give a push 90 degrees to that. there will be normal force, and there will be gravity little mg. These are two forces on block of mass m. These are two forces, and the acceleration is ax ay, and this is theta, and this direction is y, and this direction is x. So if you put those directions on top here, this direction is x and this direction is y. So if this is theta, this is 90 minus theta, this is theta, so this angle is theta. Make sure this thing you followed me properly. So the x is this, only this guy has x component, this guy does not have x component. So m times ax is just nx, which is n sine theta. So that's one equation, and m times ay will be ny minus mg. The y component is n cosine theta, so this is n cosine theta minus mg. And over here we can clearly use this, get rid of y, so this is m a minus mx tangent theta. So between this equation and this equation, if you get rid of n, I'll be home. So one way to get rid of n, just substitute from n over here. So this n will just give me max over tangent theta. So, and I put it over there. Let me, everybody has a different way of doing algebra, and I have my own. So this just looks like m a minus max tangent theta equals to max. That's not tangent, this is sine theta. Sine theta ax over sine theta times cosine theta minus mg. So that's what I was saying, you don't need m in the problem, and you can see m is in every term, so we can just get rid of m. This is every term, and ax is here and ax is here, so bring them on one side and bring everything else on the other side. So bring these guys on this side and mg on the other side. So this part will say ax over tangent theta, right? This is tangent theta, and this comes over there, plus ax times tangent theta, and this guy plus g. So ax, let's see, tangent theta, and x is common, 1 plus tangent square theta, and this is just a sec square theta, and that's just 1 over cosine square theta. So if I write this a little bit, so this is cosine square theta and sine theta by cosine theta. So one of them goes away, multiply by 2, and that becomes a cosine 2 theta, a plus g. So a sub x, 2a sub x times sine of 2 theta equals a plus g. So ax is a plus g over 2 times sine 2 theta. and a sub y is a minus this thing times tangent theta, a plus g over 2 times 2 sine theta cosine theta times sine theta over cosine theta. Cancels out, of course, 2 goes away, and the sine square theta. So this is a minus a sine square theta minus g sine square theta. And so this is like a becomes cosine square theta minus g sine square theta. So this is ax and ay. Those are components. So we actually solved the problem, but let's see, say theta was 45 degrees for simplicity, okay? In that case, cosine theta is 1 over square root 2. Sine theta is 1 over square root 2. Sine 2 theta is just going to be 1. So in that case, you have ax is going to be a plus g over 2, and ay will simply be a times half minus g times half is a minus g over 2. So you can see, depending on the values of a, this is going to be in whatever direction. So this is at, say, 45 degrees. Say g is 10 meter per second square. And let's see, a is 5 meter per second square. Okay, just an example. So maybe let's call it 8 meter per second. So the x will be 10 plus 8. 10 plus 8 over 2 is going to be 9 meter per second square. And ay will be 10 minus 8 over 2. It could be 1 meter per second square. So this is the positive x direction, and this is the positive y direction. 8 minus 10, that's how I was thinking, minus 1. So this is minus 1, and the other is 9. So you can see, if I draw to scale, 1, 2, 3, 4, 5, 6, 7, 8, 9. So the acceleration will be in that direction. Okay, so the actual acceleration will be in that direction. And you can say the magnitude of the acceleration will be square ax square plus ay square 9 square plus 1 square, and that's roughly, of course this is square root of 81, 82, but that's roughly 9 meter per second square. So it's going to be that long. It's pretty crazy the way acceleration kind of depends on if the block is accelerating or not accelerating. If the wedge is accelerating or not accelerating. If the wedge was not accelerating, it's going to be not as big. Okay. So this is a good problem. Where can people actually make a mistake in this, in thinking? So the way people can make a mistake is about the forces. That's one place they can make a mistake. Another place they can make a mistake is not think that they need inertial reference frame. Now, why do you need inertial reference frame? You need inertial reference frame because F equals to this MA, only this form of F equals MA is only true in an inertial frame. So if I were to go with the wedge, if I do X and Y attached to the wedge, it wouldn't work because the wedge will have acceleration 0 with respect to X prime and Y prime. And in that frame, equation gets modified. It's not that equation. It's a different equation. Coming to forces, when people say wedge will keep push this guy, so they imagine, many students imagine there's a force like this, which is of course not correct. If there's no friction, this was frictionless assumed, so there's no force along this, the only force is going to be normal to it. That's the only force going to be. No friction, normal is the only force. So these are two places people can make a mistake. A third place people can make a mistake is, well, I know how to do things in an accelerating elevator. I'm just going to guess around. I can guess. Actually, I can guess very correctly what the wedge, what the accelerating elevator equation will be, because I know in an accelerating frame what the F equals ma changes. But if you don't know that and you're trying to just guess from your gut feeling, that's another place that you can make a mistake. Okay, so that's all for now. I will talk to you another problem solution. Bye.